So today onwards, we will be starting the strength of material. So 1 minute. So how many of you in the graduation or completed graduation? Can anyone respond? So accordingly, I have to means go first. Whoever completed the graduation, those can raise hands. Okay. Okay. And how many of you haven't studied SOM yet? Anything? Okay, fine. So I will ask you in between. So try to respond. If anything you are not getting, then let me know. Okay. So can anyone let me know? Two things are there. One is strength of material, and another one is the in like sorry. Okay. So in strength of material, what is the aim? What we are going to study? Can anyone tell?
So, did you start recording?
Yeah, I have started today. Yeah.
Sir, in strength of material, we are going to study about strength, stability, and stiffness of the material.
And
Mm,
deformation too.
and what is the difference between in the because we are going to apply load here, right?
Yes,
So
sir.
what is the difference between applying load here and once you have studied like 1 minute, uh, you would have studied uh, in as in oh, in production, right? Metal forming, you know, right?
Yes, sir. Sir, are you asking about mechanics of material? The difference between strength of material and mechanics of material?
Just tell whatever load you are applying here and whatever load you are applying in the strength of material. So what is the difference between both of them?
Sir, in this production we are dealing in the plastic zone, and in this song we are dealing with the within elastic limit.
Uh, so major difference is here we are dealing with the in elastic zone. So elastic zone, and here in the plastic, because here you have to deform, and here our aim is not to deform, just due to load some deflection is there, but that deflection is very minimal. So plastic zone or deformation here it would be. So here in the strength of material, uh, stress strain diagram we see. Let's suppose for mild steel I am plotting. So till here, like we can say here, this is elastic zone, right? And after that plastic zone would be there. So metal forming, everything would be happening here. Huh? So that is a part of metal forming, which type of operation will happen here and which type of operation happen here. Huh? And after that, no mean. Whatever operations are happening, this will happen before ultimate point. Okay. So can anyone tell why we do not go beyond ultimate point for any type of operations?
Sir, because that would be the reason of fracture.
No, no, fracture will happen here only, right? This is the ultimate point.
Because there is a deformation without this stress. If you are not applying stress, then there will be a deformation.
Mm. So you in metal forming, we would be studying like sheet metal forming operations like punching, blanking, bending, like that, right? And here metal forming rolling, forging, extrusion, wide rung, etc., etc. So those will happen here, metal forming operations, rolling, extrusion, wire drawing, etc. And sheet metal operations will happen close to the yield point here. And after that, no operation will happen, because you know this ultimate point. And when we means mathematics, I am not going deep into that. So dp by uh, da means, after that, uh, when you don't apply any stress also, because after that, even though area will going on changing, so if you don't apply any stress, even that also material going to fail. So whatever operations we are going to do before ultimate point only. So now coming to the SOM, whatever what we are going to cover here. So first, we will going to cover various types of stress, strains, and whatever type are available, that will cover. After that, principal stress and principal strain part will go. Here we will stay for 2 classes, and here also it will take 1 to 2 class. 2 class at minimum it will take. Here 1 class will spend, and here in 2 to 3 class all type of SFT BMD will cover. And after that, reflection also take two classes. After that, here we will finish quickly, after, because this is the major part. If that we will cover, then it is the major thing will coming from here only after that. So here it won't take much time. So that's this part will cover quickly. uh, so today we'll be starting from stress and strain. Okay, so can anyone tell, like, what is the stress? Just simple definition, can anyone tell?
It is the resisting force per unit area.
So two things are important here. First one, resistance force, because also pressure also we can say force per unit area. That is not here, resisting. And one important thing you missed here. You told what you told, resistance,
Resisting force per unit area.
resisting force per unit area. But which external resisting or internal? Here it is important, internal resisting.
Internal.
So internal resisting force per unit area. So force would be the so that is the first main thing. And it depends on plane, main thing. So when we change the plane, stress will keep on changing in a particular plane. So that we will see in the Mohr circle diagram, like when plane will change, stress will change. So how much stress change with the plane, that will also depend. So let's suppose this is the one prismatic bar, and this is the cross section area. So we cannot see, like, how much stress is there. If we are going to cut it, then stress is going to diminish. So it is this is felt by the its molecule particles. So those particles are resisting that to means this force is a tendency to increase its length, but it's a particle is particles tries to not to get extend. So that resistance felt by the particle is stress. So internal resistance force. So but we cannot measure it, because if we are going to, because it is happening internally, and we cannot put any device on that. So stress cannot be measured, cannot be measured, but strain we can measure, strain can be measured. So when we measure the strain, with the help of strain we calculate the stress. Okay, calculate the stress. Got it?
Yes.
So like you know what is the tensor? Scalar, you know scalar?
Yes, sir.
What is scalar?
Yes, sir. Which only has direction,
Those properties
direction,
those
but
properties
vector
which we can define just by providing the magnitude only, right? that is like degree Celsius.
Yes,
It
sir.
is complete significance. Has
And
vector.
and
Huh?
and vector has both.
In vector, in order to make it significant, we have to provide magnitude as well as direction. So for the scalar, only magnitude is required. Now coming to the tensor.
So scalar is a zero order tensor, sir.
Uh-huh. Zero order, first order tensor. I will show what is the meaning of tensor.
Yes, sir.
So
Okay, sir.
what is the second order tensor? Because stress, strain, moment of inertia, whatever we are going to deal here, it is the second order tensor. Hmm? So what is the second order tensor? In second order tensor, magnitude and direction, as well as one another thing will depend, because here apart from magnitude it depends on two other things, direction and some other. Here plane will come into picture for the stress. Which plane? So apart from magnitude, what other properties, how many other number of different things are needed to completely signify that? It depends, that shows the which order tensor is that. So in stress, strain and moment of inertia, other things are we needed, direction and plane. So second order tensor. And vector, only apart from magnitude direction is needed, so first order tensor. Scalar, on apart from magnitude nothing needed, so zero order tensor, right? So that way we can say. Now here, how we defined the stress? Internal resistance force per unit area. So if it is internal resistance force per unit area, then for any material, whatever material we will take, like one we will take steel, one will take plastic, and one we will take, let's suppose, iron. Iron, steel, we can say same. Titanium, we will say titanium. So now we'll apply the same force P, and its cross section area is the same for all. So stress would be the same in all, right? Hello.
Yes,
Yes.
sir. Yes, sir.
So stress would be the same in all. So what conclusion came from here? Like stress is not a property of material, right? Stress is not property of material. So can anyone now coming to the strength? What is the strength? Can anyone tell?
It is the capacity of the material to
Hmm.
withstand the load.
So it is the capacity of. Am I audible, right?
So maximum stress the body can.
Yes.
Same thing, same. In other words, we can say maximum load that body can withstand without failure, right? Hello.
Yes.
Yes.
Same thing,
Yes, sir.
capacity
Yes,
of
sir.
any material to withstand load without failure. So now here, so what would be it will be the property of material, right? Because now we'll take steel and plastic, it will fail at different loads. So strength would be the property of material. Property of material. So now one another thing, like stress and pressure. Because stress is force per unit area also, and pressure is also force per unit area, right? In all all direction perpendicular to the surface, right?
Yes, sir.
So what is the difference between this? Can anyone tell?
Pressure is normal to the
Sir,
and
One by
stress
one.
will be in the plane.
What are you saying?
Pressure will be sir, pressure will be normal to the surface. Yeah,
Hmm.
it will act normal to the surface.
Hmm.
Pressure
Okay,
and
perpendicular to
stress.
surface.
Yes,
Hmm.
and stress on any plane.
Any plane.
It
Okay.
may be perpendicular plane.
Hmm. Then
and one thing we could say by using by saying in terms of tensor that pressure is zero order tensor and whether stress is a second order tensor.
why pressure is known as zero order tensor? That is the first question.
Uh, as sir, it only act upon an on a, like on point like
Why
sorry
current?
sir.
Why a current has magnitude and direction both, right?
Yes
So
sir.
why current is scalar?
Magnitude and direction.
Only one reason is there, because that follows the scalar addition, right? Because two currents, whatever direction it will come, like here it is coming and going, uh, whatever angle between that current here, if 4 ampere here, 3 ampere here, here only 7 would be there, whatever angle is there. So it follows a scalar law of addition, not vector law of addition. That's why current is scalar. So
But
same happens with pressure. Whatever pressure is there, it is the it follows the normal addition. So
hmm.
if doesn't follow the vector addition, so it is the scalar. If scalar, so zero order tensor. That's why. So another difference, what I was telling anyone?
We can measure pressure but not stress.
This one. Oh,
So can you explain that again? The reason
what reason?
that zero pressure and stress.
Not getting. What are you saying? Can you repeat?
Sir, the stress is a second order tensor and pressure is first order tensor. That
Pressure is scalar, zero order tensor, because pressure, whatever pressure is there, if we apply pressure 4 bar something somewhere and 3 bar somewhere, and so if directly is going to merge, then it directly we can add pressures, right? It depends on angle. It is pressure we can add directly, right? Because direction is always same, perpendicular to surface. Hmm.
Sir, pressure is always compressive type.
That is one type of stress, because first here we'll write can't be measured and it can be measured. And pressure is
Since a scalar addition is followed, it is a scalar quantity.
what?
Since pressure follows scalar addition, it is scalar quantity.
Yeah. Only due to addition we will see, because same with current example I given na, same way. So pressure is compressive in nature only, and stress can be anything, right? Compressive, tensile, shear stress, any type of hmm? Tensile or compressive or shear, anything can be here. And another difference,
Pressure occurs
Sir,
external to
at
the
a point,
system, stress is internal.
so we can say here same thing na, can be measured, can't be measured, same way, same thing we
sir,
can say.
pressure at a point will be having the same value in all the direction.
Hmm. So pressure, because in any direction we'll measure, it will be the same, right? But for the stress, if we change the direction, it will be different. So will different at a point in different direction. Here it will be same. Any other or done? Hello.
Stress, without strain, stress will not happen.
So I'm just asking about stress and pressure difference. So
सर
same.
ये सर वैसे जो इन्होंने अभी वाक्य कहा, क्या ये सही है? विदाउट स्ट्रेन स्ट्रेस कैन नॉट हैपन।
Without strain,
स्ट्रेस कैन नॉट हैपन, क्या ये वाक्य सही है?
we will see in the thermal stress, like there we can see generally it will not happen, but if for exception case will take, then that time it will happen. Okay, generally it will not happen.
सर जैसे मैं एक क्वेश्चन पूछता हूँ सर, एक रिजिड बॉडी है, मतलब बहुत रिजिड है, मतलब उसका शेप चेंज नहीं हो रहा है, और हम पॉइंट लोड अप्लाइड कर रहे हैं उसमें, तो क्या उसमें स्ट्रेस जनरेट होगा? क्योंकि रेजिस्ट तो वो कर रहा है।
If body is rigid, right?
हाँ सर, मतलब कोई डिफॉर्मेशन हो ही नहीं रहा, कितना भी लोड लगा लो, और तो उसमें सर स्ट्रेन तो है नहीं, तो और स्ट्रेस होगा क्यों? क्योंकि वो रेजिस्ट कर रहा है, तभी उस शेप में बना हुआ है। तो सर मतलब
first, so like how it is the body, like that way we can think of.
सर एक क्यूबिकल बॉडी है, वो एक टेबल के ऊपर रखा हुआ है।
हेलो।
हाँ सर, हाँ सर।
देन
मतलब ऊपर से फिर पॉइंट लोड लगा रहे हैं पी मैग्नीट्यूड का।
हाँ
तो सर उसमें
हाँ
देन स्ट्रेस कितना जनरेट होगा बॉडी में?
then it is simple ना, if you put on the table, then if you put force on upside, then reaction from downside, it will stress would be there then that time ना।
सर तो उस स्ट्रेस का मैग्नीट्यूड क्या होगा सर? मेरे से इंटरव्यू में पूछा था ये।
ओनली पॉइंट लोड दे आर अप्लाइंग।
हाँ सर, और वो केवल डीए एरिया मान लेते हैं पॉइंट लोड जो लग रहा है, और क्यूब का साइड है, मतलब साइड मान लेते हैं एल।
तो at that time you are applying pressure, then stress would be there ना। It is completely rigid body, they told.
हाँ सर।
Sir, if it's a rigid body, so will the Young's modulus will
infinite,
be infinite, and the stress will be infinite. So
no, deformation we can say of it would be zero, because it is rigid, so E would be infinite, PL by AE, so deflection would be zero there. Means any deformation would be zero, but stress would be there.
How to quantify it, sir?
P by A stress would be there, but what I said, what would be the zero? Like 1 minute. This is the body, let's suppose. Table, okay, got it. So here it is a force, and it's a E would be the infinite, right? If it is rigid body is there. So this is P. Stress would be there. Stress is P by A. Let's suppose this uniformly load is there, so P by A would be there. If a very small portion you are applying, P by D, dP by dA, then you do.
और सर मतलब मैं पी फोर्स लगा रहा हूँ ऊपर से और डी एरिया में, पर नीचे से तो पी लग रहा है पूरा यूनिफॉर्मली डिस्ट्रीब्यूटेड एरिया में, तो तब मतलब ये तो थोड़ी एनिमली हो गई ना।
Oh, here you are saying only point load. I said like uniformly I distributed.
नहीं सर, यहाँ ऊपर से तो पॉइंट लोड है, पर नीचे टेबल के ऊपर रखा हुआ है ना, टेबल से तो यूनिफॉर्मली डिस्ट्रीब्यूटेड लोड आएगा या फिर पॉइंट लोड आएगा।
तो stress, you are finding stress only this point, right? Or if you are finding from downside, then it would be PA, because stress depend on I mean.
Okay sir.
So plane to plane stress will change now. Here every plane stress going to change. Got it or not got? Getting or not getting?
Okay sir.
Here stress would be different in another plane. Loading would be changed. So means stress got changed on the different planes. So here would be P by A, and here now you are saying like zero area it is acting, so here stress would be infinite now because area is zero now. So from P by A to infinite it will change from plane to plane if this that way you are going to see. Getting or not
Okay.
getting? Like here
Um,
P by A in plane, this plane change, this plane another, this plane another. Plane to plane it will change now, na? Because
okay,
loading is
sir.
changing on each plane.
Ji, sir.
So that way we can say.
Okay, sir. Thank you, sir.
So now we will
Sir,
see.
even in a rigid body, the stress is developed, sir.
Stress would be there because but formation won't be there.
That is because of Young's modulus being infinity, sir.
What would be the deformation? Like its a length is L, so if the load is constant, so delta L would be what? PL by A, right? So E is infinite here. So delta L change in dimension would be 0 because of this making it infinite.
Sir, if Young modulus is high, then how could it be? Could we say that that's a rigid body? Because if Young modulus is high, then the elasticity would be high for that material.
What do you mean by elasticity? Elasticity means you don't think of elastic. You stretch it and it comes back.
No, sir. Like for iron and like the elastic material, I mean rubber band. Uh,
You
between
are saying
between
like
them,
E is high, huh? E is high means
yeah,
like this is the graph
yeah,
sigma epsilon. E
yeah.
high
That's what
is
I was.
this is the one. This is second material. This is the third material. Hmm? Hello.
Yes, sir. Yes,
Yes,
sir.
yes.
I'm listening.
First, second, and third. So now which material is have more elastic Young modulus? Third, right?
Third one is
Yes,
third.
yes, sir.
So what does it signifies? Means in another words, E is nothing but d sigma by d epsilon, right?
Yes, sir.
So if E is high means this slope would be more.
Yes, sir.
Slope would be more means if E is very high means change when change in stress, change in epsilon this
For
this
small
or
deflection, more
very
stress
small
will
change
be.
in strain, there will very large change in stress. Means if you increase a very large amount of stress, even though there would be no strain. That is meaning of high Young's modulus. Getting or not
Okay,
getting?
sir. Yes, sir. Yes, sir.
And what stress
Actually, as
signifies?
actually, as you told that E would be infinitive, so therefore I thought that it would be
No.
high.
Infinity means yeah, this line
Yeah.
only. Huh?
Okay, sir.
So this
Okay,
means
sir.
whatever stress you are applying, no strain would be there. No strain means no change in the dimension.
Ha. Now I got it. Got it.
Okay. So now FPD etc. I suppose like everyone knows, right? So FPD means no supports would be shown, and we and body would be at the equilibrium with the help of other reaction forces. Okay. So first we'll try to solve this question, and then we'll proceed. I think here I have already put this question. Okay. You try for 1 or 2 minutes, then we'll solve. Is it visible, everyone, right?
Yes, sir.
So this is the one uh, one body, and here it is in the two parts. You also find here it is very easy. Let's suppose this is section CD. So stress at section CD also we can find. This is bit easy. Either before this I want to tell one more thing. So let's suppose one body is there, this is the center line. Okay, so one force is passing from here and its cross section area is A. So what would be the stress here? Any cross section if it is prismatic, so sigma would be P by A, right?
Yes, sir.
And if it is not passing through its center line, let's suppose some force is passing from here, so first you have to shift that to the center, and equivalent amount of moment we can apply, and then we'll do. Okay, for example here what will happen, uh, we will shift this to the center P, and let's suppose this is the of dimension diameter T. So what will be the moment due to this shifting of this force to here? P into D by 2, right? This way moment is there. So P D by 2, this moment would be there. And stress due to moment, anyone, what would be the bending stress, right, due to moment? What is the value of stress?
Sir, which stress? This bending.
Due to bending.
Sir, it will be 6P upon BD.
My by I, right?
6P upon.
You are telling answer, but this is My by I. So moment you can get, and Y is the if let's suppose your cross section is this way, this is the cross section, so this would be the neutral axis that we'll see in the later, and the moment of inertia and all, so there we'll see. So it would be the from the maximum distance, so it would be the d by 2 here, y would be it, and moment of inertia I suppose you know for the circular and rectangular cross section. First I will tell first one more time. So any direction x or y, moment of inertia for this is pi d to the power 4 by 64, right?
Yes, sir.
Ixx or Iyy, and for the rectangular, let's suppose this is d and this is b, xx, y, y. So Ixx would be b dq by 12, and Iyy would be dbq by 12. So this way try to solve this question. After 1 minute I will solve. Whoever did, then we can solve after the 1 minute. Anyone solved?
Yes, sir. I have solved, and I am getting this overall bending stress at the bottom in AB section is 8P upon BD.
Total stress or only sigma b?
Sir, overall bending plus this tensile.
Okay.
Tensile will be 2P upon BD.
Okay. Total you are getting 8P by BD, right?
BD, yes, yes.
Okay. So remaining can solve for 1 or 2 minutes, then we'll start.
So we can individually add the stress components.
Yeah. Because both are normal stresses, right? Tensile stress and bending stresses both are normal stress, and shear stress like torsion or that will come into the shear stresses. So normal stresses we can add, because in bending what happens in one portion, this way variation would be there, right? Let's suppose this is the cross section, so in one direction it would be the tensile and one direction it would be the compressive, and magnitude would be the same. This would be the neutral axis line. So let's suppose here positive and here negative. So whatever would be there, here maximum positive and here same value maximum negative, right? Getting or not getting this point?
Yes, sir. This is a deformation, sir.
Distribution of stress on the bending stress on the cross section.
Yes, yes. So
actually,
since both are normal, we are able to add it.
Yeah. So because it is tensile stress would be anyhow positive, so maximum would be the upper side. If this I will solve, then we will show how we can. So first of all, we can divide this body into three parts, like one is this, and second one in between, and third one is this. So first part we can easily distribute the load. Yep, P, and easily stress on the sigma CD is P by, let's suppose, uh, this P by BD. Now coming to the this part, first stress is this way, P P. Now we have to move this load to the center part, so we'll do that. P, and moment will come, and value of moment would be P into D by 2. Then the
Our moment will be
D
PD
by
by 4 na, 4 na, because it
sorry,
will
sorry,
act
sorry,
at
at D by 2, P D by 4. Okay, it will be P D by 4 because it is D by 2, so half we have to go there. Now direct stress sigma T would be P by this is B, and this is D by 2, so D and 2 P by BD. And now coming to the sigma B My by I, M would be PD by 4, and Y would be because this is half, and uh, let's suppose
D by 4.
D by 4, D by 4.
so this is D by 2, and from mid it would be the D by 4, so it would be the D by 4, and I would be
BDQ by 96.
BDQ by 96. Now we can simplify, it would be the 6, so it will become DD
6P by BD.
6P by BD. So in the AB cross section, two things that may ask, like what would be the sigma AB maximum and sigma AB minimum, both may ask. So maximum would be how much? Because
8P by BD.
because
Yes.
what would be the variation, like due to that this direct stress, it would be like this. Let's suppose this direction is the this magnitude will be the same here, not same showing, and plus so resultant of that will be the our answer. So here this plus this both will increase, and here this is positive, this is negative, so it will decrease. So maximum would be the addition of this and this, means sigma B plus sigma T, and here sigma T anyhow positive and sigma would be negative for minimum. So here it will become minus 4P by BD, and here would be the 8P by BD. Now we may add here values, so answer will come into the numericals, so that keep in mind. So maximum minimum both may ask. Okay,
So here additionally, if we had shear stress, we cannot add directly.
what
Here additionally, if we have shear stress component.
where we have shear stress here?
No, sir. Generally, I'm asking if we had additional load such that if we have stress, we cannot directly add those.
No. That time we can't. That time if shear stress also will come, then more circle etc. will come into the picture. Then.
Yes.
Sir, again, once again, explain, sir.
What? This question we want, na?
Yes, sir.
So this till this we have taken the mid part, right? First part this is easy till now, till here, because here what we did, we took this portion. Let's suppose this is 1, 2 and 3 and 4. Either 1 2 or 3 4, this would be the case for 1 to 2 or 3 to 4, because their force is acting on the mid part. So directly stress would be the P by BD, because B is this and D is the its depth. So this would be the stress. And now coming to the mid part, the loading condition is like this, right? Hello.
Yes, sir.
So now we shifted the load to the center. When we shift the load to the center, then a moment will come, because shifting of load. So when we shift load from here to here, how much moment will come? P into this distance. This distance is how much? Because this is d by 2, so this is half, so d by 4, P into d by 4. This way moment will come. And now two stresses, due to the bending also stress will come, and due to the direct loading stress would be there. So due to the direct stress loading, this would be the stress, because P by B d by 2, because this is d by 2, right? Width, sorry,
Right.
depth, and width is B. So B d by 2 and 2 P B D, it would be the direct tensile stress. And now calculated the bending stress would be the My by I. M we have directly here, and Y is the d by 4, that I have shown here, and I is the this B d cube by 12 we will do, but D here is d by 2, so it will become like this. So when we solve it will happen. Now this is important here for maximum and minimum, because this direct stress distribution would be the same across whole the cross section, but the distribution of the this bending stress will change from same tensile value to compressive value. So this we have to accordingly add and subtract. So for maximum, both value would be the positive, then only maximum would be there. So bending is 6p by BD and tensile is 2p by BD, so it will become 8p by BD. And for minimum, it is tensile and here it is compression, uh, so it would be the minus 4p by BD. Okay.
Thank you, sir.
Try this question once. First try to make FBD and then try. Trying right or not?
Sir, it is 2.
No, sir, 4.
Okay, any other answer? 2, 4, 2, 4. Any other? Any other answer?
Two, sir.
2.
Yes, sir. Two.
Okay, then more answers are coming, so we'll wait one more minute and then we'll see. Okay, now we'll start. So for if there is any support is there, so try to make FBD from the free end. Okay, this keep in mind. So we'll start FBD from here. First we'll draw the BAC part. Here F is there, and here we'll apply force F. It's E B C. Now here net force would be the P in this direction. Hello.
Yes, sir.
Anyone is saying anything?
No, no.
So in order to make that effective force P in this direction, what we'll do? P minus F, because this is the attached part. When we'll add, so FF will got cancelled, right? So net force P will come. Got it or not?
Yes.
If any problem till here, let me know. P minus F, same force will come, and 3E. Length is L and L. So one is in the one part is in the tension and one part is in the compression. So in the question, what is saying, a horizontal bar constant cross section is subjected to the loading as shown in the figure. The Young's moduli for the section AB and BC are 3E and E. So for the deflection at point C to be 0. Here no deflection should be there. Means this point should be at the same place. So when it will happen? It will happen when the compression, wherever compression is there and wherever tension is there, both would be the same. So deflection
would be 0.
Deflection delta L would be 0, but what would be the delta L? Delta L would be the delta L of AB plus delta L of BC. But I forgot to give you the formula for the delta L here, because what is the Young's modulus is stress upon strain, and stress we know, stress is force by area, and strain is delta L by L. So from here we can get the delta L. Delta L would be what? PL by AE. If area is not changing, then we can use that formula. If area will be changing, then we have to go some another way. So now we will be putting this. So for this, this part, P would be the P minus F, L would be the L, and A and E is the 3E. Okay. And this should be the equal to this part, F L by AE. Hello.
Yes, sir.
So LL will get cancelled and AE will get cancelled. P minus F would be equal to 3F. So P would be equal to the 4F, and what we have to find? P by F. So P by F would be 4.
4. Yes, sir.
Any problem?
Sir, in A to B diagram, the direction, force direction, why it's internal, sir, and fixed?
What are you saying?
Sir, in fixed, at the part of the fixed, the force is in the direction of the block only. Why it is opposite? Why it is not opposite?
You are saying y direction means this also in tension. You are saying like that, huh?
Sir, that part.
Actually, what are you saying? This I have shown this way, this figure. Means it is in the compression. So what are you saying? It should be in the tension.
Why it is not in tensor?
Because see this junction. So what will the direction of force here? This way.
In compression.
This way. At the junction, net force would be here. But I have started from here. So F would be this way. And now forget this. Forget this part. This part forget as of now. So at the section B, what is the net force? F force in this direction, right?
Okay, sir, I got it.
So we have to make net force here. If you are saying like we will make this way, then you have to do some another work. And then now the,
So,
after so after
sir,
here
we
you will
can.
change the sign.
Sir, if we solve the problem with f minus p, then what would be occur? Because how will we understand that p is greater than f?
Same answer will come
Compre-
F for by taking this intention. F minus P. F minus P, if we take intention, then same answer will get 4.
yes.
What are say?
What,
Hello.
sir?
Sir, I am saying
Actually,
that
I was taking.
Uh-huh.
Actually, we did the problem p minus f. Then if we did it f minus p, then what problem will we occur?
then it will be
Minus p
intention.
you are saying, then I haven't took this na. I have taken I haven't said like take fp minus f. I just took the direction of here. Don't think from your side. Whatever in the figure is there, you try to do that. For the in the same way, I will try to give one or two more problem. Let's do the same, and then you will see like we need not to think directly. Whatever is shown in the equilibrium diagram, that we have to do. And question would be correct. 1 minute. Only for forward distribution, I will give this. 1 minute. Let's suppose this is there. Sorry. Here A, B, C. Here would be 100 kilonewton is there. Okay. Here 350 is there, and here 250 is there. Now how will you distribute? Let's suppose I remove this at 350 from here. This is there. Same problem, right?
Yes, sir. Yes. Okay.
In tangent only. A and B also tangent and B and C also tangent. From
Yes,
B
sir.
to
In BC, we can take this tensile 100 kilonewton and AB 350 kilonewton tension.
What I said like if support is there, keep this word in mind. If support is there in one end only. If in both end, then no option. You have to take one reaction. No issue. If support is there in one end, then always start making FPD from free end. Okay. Don't try to start from this way. Otherwise, you have to. If you want to start this way, you have to suppose one reaction, right? Because you don't know what reaction is there, how much. And if you start from here, you will know the value of reaction automatically here. Let's suppose, for example, I'm not going to solve this. Just I for practice purpose I will give it. If because in free end 100 is there, so anyhow to make an equilibrium 100 would be here, right? So 100 here. Now net force would be 250 here, but 100 already came here. So in this part, make to in that junction make it 250 this way. You have to put 350 this way, right? Because 350 and 100 it will come 250 net will be here. Now in to make it in equilibrium 350 would be here. Correct? Hello.
Yes, sir. Yes.
So this way you have to do. Okay.
Ah.
Now where are we? Okay. Now coming to the what is the engineering stress and what is the true stress? Anyone can tell?
Sir, in engineering stress, we take load upon this original area, and this true stress we will take instantaneous area.
That is okay. In engineering stress you are saying like sigma naught we will simplify it. It would be the P by A naught. Let's suppose this is the our initial. It would be the L naught and P we applied and its area is A naught, and after the application upload it became like this AF, LF and P, right?
Yes, sir. Yes, sir.
This is the case. So engineering stress would be this, and true stress would be the P by AF, right? So
Yes, yes, sir.
so in strength of material, we go for this only. Why? This is the question.
Because sir, in this we are dealing in this elastic zone, so area will not change much more.
Mhm. So error, if we use this, then error in the answer would be less. So it is comparable. Let's suppose because in this stress we are going to use in the deflection. How much deflection is there? We see deflection there. So if we are going to, let's suppose this is the beam and this diameter is 80 and initial diameter, and final diameter when applied load and etc it will become 79. 1 mm deflection, 1 mm change in the dimension is there, but if we take the true stress the calculation would be very difficult, because at any instant diameter would be changing, keep on changing. So to monitor that is very difficult, and also calculation would be very tough. So and error also is not much, because if deflection you are going to get from 80 is 2.44 mm, let's suppose, and with 79 you will get 2.42. So that is not that much difference there. So that's why in strength of material, because our loading condition is usually in the elastic zone, so due to the low loading condition we can use this, because and error in the answer our is very comparable to the actual answer. So that's why in strength of material we can go for this, but in the metal cutting and metal forming portion we will go with true stress only. Okay, but here let's suppose any problem is designed specifically, but written in the strength of material like steel body they have given, but they have given significant amount of change, then that time you have to take true stress, right? Got it what I'm saying or not?
Yes.
Hello.
Yes,
Yes,
sir.
sir.
Yes, sir.
Hmm. Okay, so can anyone tell Hooke's law?
Sir, within elastic limit, stress is within proportional up to proportional limit, stress is directly proportional to the strain.
Hmm. Actually the this is up to like sigma and this.
Within proportional limits.
Yes,
Actually, let's suppose this is the proportional limit, and after this is changing. But actually, when this Hooke's law has been defined, then at that time it has been said like till elastic limit. Okay, stress is proportional to strain, that way. But actually, it is till proportional limit, right? So ideally means in theoretically it is till elastic limit, Hooke's law, but practically it is still proportional limit. So that is the difference that we can take. And this is for normal. Uh, when this proportionality constant will go, sigma and sorry E will come, and for the shear stress gamma would be there. This is the shear strength, right? So tau is equal to G E sorry G gamma modulus of this is rigidity, and when we apply the pressure delta P, some change in the delta V by V, volume change would be there. So when we apply pressure, bulk modulus will come into the picture. So these three things would be there. So now Poisson's ratio. What is the Poisson ratio?
Sir, lateral strain, it is the ratio of lateral strain upon longitudinal strain.
Poisson ratio mu is the minus epsilon y by epsilon xx. Why this minus came here?
Because sir, if you applied load in longitudinal direction, then there will be a reduction in this lateral direction. So finally, final minus initial will come negative.
So to make it positive, right? Value mu. Because in if we increase any length, so its diameter or width will going to decrease. So in another direction, it is going to be negative. So for example, let's suppose this is the initial condition, and when we applied load, it becomes like this. This is L naught, and this is the LF, and this is the D naught, this is the DF. So what would be the epsilon YY? This D naught minus DF, right? By D naught. Hello.
Because sir, we have taken negative sign.
So and same we can calculate like longitudinal strain and and lateral strain, and the ratio of that would be the Poisson's ratio. So generally the value of Poisson's ratio will vary from the -1 to 0.5, but in practically it what Poisson's value negative, what it signifies? It signifies like if you increase the dimension one side, another side dimension will also increase. Like balloon is there, so you are increasing it, and in same way whole all sides it will increase. Means if you some any practical example is not there for the minus Poisson ratio, but so practically that's why practically it is from 0 to 0.5. All materials are in the positive side. So now four things have came like E, G, K, and mu. So what would be the relationship between E, G, K, mu? Means all these are the constants, right? And constant for material. So material constants are there. So can anyone tell what is the relation?
Sir, it is E is equal to 2G into 1 plus nu,
Hmm.
3K, 3 is equal to 3K, 1 minus 2 nu is equal to 9 kg upon 3K plus G.
So it is valid for keep in mind here any two proper how many property you needed here? Two or three?
Sir, two properties.
So here any two property, if you know any two property, if you know can be found remaining two, right? Hello.
Yes, sir.
Yes, sir.
So, but these formulas are valid for the these formulas are valid for the only isotropic material. So, what can anyone tell what is the difference between isotropic and homogeneous?
Sir, in homogeneous, in a particular direction, properties remain constant, but in isotropic, at a particular point, properties in all directions remain constant.
No. So, for isotropic, what you told? At a point.
At,
Hmm,
at a point, in all directions, properties remain constant.
properties will be the same this way, right? But let's suppose this is the material, and here properties are this, and here properties are different. Let's suppose it's less property, but same in all direction, but less than this, right? This way. And here also in between both, like more than this and less than this, like that. But here it is same. So this is isotropic or not?
Yes, sir, it is isotropic.
Anyone saying anything else? Let's check.
No, no, sir.
It is isotropic because in isotropic you have to see only one point. In if that in that point in all direction properties are same, then it is isotropic. And same for homogeneous. Like let's suppose this direction we have chosen for different points we can say, but direction would be same here. Any point we'll choose, but in this direction properties will be the same. But in this another way, if this direction this much is there, but it would be the same, so it is homogeneous, right? Hello.
Yes, sir.
Yes, sir.
So if we say like isotropic and homogeneous, then it would be the same in all direction, all point, and all points and all direction it would be the same. Got? So so 2 3 things are there that keep in mind. Like one is the isotropic material. What is the isotropic material? Properties would be the same at all direction at a given point. So minimum number of independent variable requires to define all the properties of material is 2. What is this? Minimum number of independent material properties required to define all other properties. So for the isotropic we needed only 2, because here we saw like if any 2 property we know, we can define all other. And for the orthotropic, what is the orthotropic material? Can anyone define?
Sir, its properties are different in different direction.
So no, orthotropic I am saying. What is the orthotropic? Not anisotropic. Anisotropic you are saying. Hmm? In anisotropic, properties would be different at the different direction. Huh? Hello.
Yes, sir.
So for the anisotropic materials, number of independent variables, material property variable we needed is 21. So 21 variable material properties we needed in order to define whole. And for the orthotropic materials are the materials in which, let's suppose this is the material and this is the point inside material. So any perpendicular directions, this or this, and this direction also, or we rotate this any other perpendicular direction. Let's suppose in this same material, this way we are taking. Got it, na? Perpendicular, but in any orientation, it doesn't matter. but in perpendicular direction properties are same. Orthotropic means 90 degree. So at 90 degree material properties are same. So at that case minimum number of variables are 9. Okay, so that you have to learn. If any time it will come, then you can.
So for isotropic, at a particular point, all the properties will be same. Then for another point, so for isotropic, at a particular point, all the properties are same, and
All
for
direction,
another
all properties are will be same.
for another point, it will be different. It
Yeah,
can
yeah,
be
yeah,
different.
yeah. That I shown only here.
Okay, sir.
Another point it may be different, so no issue. Okay.
Okay.
Now, what is there? This same question I think here also we have to do. We can easily do this. Till now, what one thing is one part is opened till now, but here what happened? Both are closed. Both are fixed. So what we have to do? I said if both are fixed, then we have to assume the reaction at one side. Let's suppose this is AB. Let's suppose this we are supposing at RA. RA here and RA would be here. And now net would be the 10 this way. So 10 minus RA. And same way 10 minus RA. But it is rigid, so net deflection would be 0. Now simply we can do, right? It is the length of 1 and 2, and P L by A and E are both are same material, so we can say like AE, and these and plus 10 minus RA.
So it will be 10 plus RNs because we are considering compressed.
What?
Won't it be plus RN?
No. You don't worry about that. That will because oh, 1 minute.
So we considered RA as compressed.
Yeah. 10 plus. Because when will we add, then it should come 10. Yeah. So it would be the 10 plus RA. Yeah. So PL by AE, it would be 0. But here it should be the minus, right? Because here compression is there. Here, both are compression I have put. So RA and this value will automatically take care of that. No worry. RA plus RB would be 10. So what would be the value of RA from here?
Sir, 20 by 3.
RA would be
20 by 3.
Plus it is coming, right?
Yes, sir. It will be tensile, I think.
So 20 by 3 means
Tensile, yeah.
And simply put the RB we need not to write here because directly 10 plus RA it is coming.
10 plus RA.
We can find both way RA and RB both we can find. What is the value of RB?
10 by 3.
Okay. 20 by 3 and here 10 by 3. So this way we can do.
Sir, how it is, sir? 3, sir?
Huh?
How it's 3, how it's, sir? AE value?
Not getting. What are you saying?
Means 20, okay, sir. By 3. 3, how it is, sir?
No, you just simplify it. Na? AE will, here will in 0 it will come, it will go out, and here minus RA,
mean total length. Actually, sir, he is asking about the total length. I'm as far as I took.
Which total length?
Actually, the three, two.
No, here you
Oh,
are
oh,
confused,
oh.
right?
No, 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 no. Uh,
PL, L is the length of this part, of this part. So this is L. So we will just simply multiply this 2 RA and RA. It's coming opposite here.
so that's what I told that.
Sir, RA will be minus 20 with it.
Yeah, minus 20 by 3 it will come, right? Minus 20 by 3. But whatever we supposed in our assumption, that is wrong. Okay, means we have taken here as a compression, right? So it is not a
Sir.
compression. Actually, it would be the tension, but magnitude would be this. That you have to say, right? Got it or not?
Yes, sir.
Here we have assumed like this first part is in the tension compression, like A B, but actual condition would be different. Same here we can put minus 20 by 3 will put and we get, right?
Sir, how it's a 3 A value area?
Huh?
Area how much, sir, in this case?
Area A area we have taken for all same. A is same and E is same for both. So that's why AE in both I have took.
Okay, sir. Okay.
That's why it has gone here and finished. Clear it or not?
Yes, sir. Clear.
So we'll do the theory part of the thermal stresses today, and numericals will do next class. So one is the first we think of the free expansion. Let's suppose there are three types of problem in the thermal expansion. One is free, and another one is the permitted expansion problem, and the third one is the spring. So three problem we will see here. So in free, let's suppose this one rod is there, no resistance is there. So its length is L, and let's suppose delta T heating we are doing first. So we know the coefficient of thermal expansion alpha is there. So as temperature increases, its length will increase. So now how much length will increases with delta T temperature increase and alpha is the this, then delta L is L alpha delta T. That we knows, right? Hello.
Yes, sir.
So this much length is L alpha delta T. So, but is there any resistance to this deformation?
No, sir.
No.
No atom has experienced any resistance because no one is going to stop this deformation. So here thermal stress is not non-zero, means thermal strain is there because its dimension has been changed, but thermal stress is zero, right? Hello.
Yes, sir.
So this is there, and same way, how much strain is there? Delta L is L alpha delta T. So strain would be the delta L by L. It would be the alpha delta T. This much would be the strain, right? Hello.
Yes.
Hmm. So same way we can do for the cooling, correct? Because in cooling it will compress, and that we can easily find. That I am skipping. And third one is the hmm, let's suppose now another case is here we have fixed. L is the length. Now its length is not going to change, but let's suppose we are increasing the temperature. If we are increasing the temperature, then its tendency to increase its length, right?
Yes, sir.
Let's suppose this is L alpha delta T, but it won't be able to do because of the supports. Hmm? So strain won't be there because these supports haven't allowed it to get expanded. Hmm? But but what happened? This much strain has been restrained by the supports, right?
Yes, sir. Then,
So
sir, won't that face a bending moment or like that when it has a tendency to
that
increase?
depends on material property. If a material properties are
Okay.
poor, then it will got bend. If a material properties are better, then it is
Mm.
directly normal stress, normal compressive stress would be there like
Uh,
that. Huh?
uh,
So that we need not to think of as of now. Just like it would be the stress now stress would be there. That is the main problem thing. Huh? So what is the thing? Actual length should be this much, but now only this L is there, and it actually if no support would be there, then if this length would be L plus L alpha delta T, right? Hello.
yes, sir.
Hmm. So now the length is how much length has been compressed L alpha delta T, and this much compression is given by the reaction from these supports, given or not?
Uh,
Yes.
sir.
Let's suppose this is A and this is B. So what would be the value of R? This would be the PL by same PL by AE, correct?
Yes, sir.
So from here we can easily find the value of mm, R. If it is asking for R, then R also we can find from here. And if it is asking for the stress, then R by A is the thermal stress, right?
Sir.
So R also we can find, but if asking for thermal stress, then thermal stress would be the LL will get cancelled. So alpha delta T and E. So in the here how which type of stress would be there? Compressive or tensile?
Compressive, sir.
So compressive. So if when temperature will increase, then compressive stress would be there. When temperature is increased, decreased, then tensile stress would be there, right?
Yes, sir.
And now one another case like this is the case like it is the free body. Now here what we have seen, if body is free, no support is there and body is free. But here what is the condition like temperature? If here is 100 degrees Celsius and here 110 degrees Celsius, then it is for the whole body, right? Here 100, here 100, here everywhere 100 degrees Celsius, right? And here and the downside 110 at every place. Okay. Now what is the condition like at this end? Let's suppose 200 degrees Celsius temperature is there, and at this end 250 degrees Celsius temperature is there. Got my problem or not?
Sir.
So here what is the body is free, no support and nothing.
Body.
But here same, here also no supports, but temperature gradient is there. So this temperature gradient means here 200, here 201, 220, 225, like that 250 it will come. Hmm? Hello.
So the change in length keep on increasing with each cross section.
What?
So the change in length will keep on increasing.
Temperature will where temperature distribution, some distribution would be there, right? So now what will happen? Like
वो thermostat will become zero.
what?
How the thermostat will be zero?
Not getting. Your voice is not able. What is it?
Thermostat is equal to zero.
No.
How it is?
Now here no thermal stress is zero. Na, that's why I said. So what will happen? Like here temperature is, let's suppose, 210 degree Celsius, and just close to that, what would be the thermal temperature? It would not be 210, right? 210 point, let's suppose, 5. This would be there. Some difference is there, right? Hello.
Yes, sir.
So due to this temperature difference, so this particle would be means the some different energy difference is there. So these particles are means some internal stress would be there. Internal stress type of thing would be there. Internal stress. Stress is what? Stress is nothing the internal resistance. So if this is another different temperature, this is a different temperature. So tendency to repel or attract is different. So due to that, internal stress will develop. Okay. So this whole body is internally stressed.
So here stress is developed due to the temperature gradients.
So if it is written like if temperature gradient exists in a body, then there would be the internal stress. The internal stress would be there in the body. That we can say. Got it or
Yes,
not?
sir.
Yes.
Sir.
Someone is saying anything. What are you saying? Hello. Hello. Is someone asking or what?
No, sir. No, sir.
Okay. So we'll say, take the thermal stress with the permitted expansion. That one simple case we'll take and stop for today. And next class we'll solve the problem with the permitted expansion. And
So in the previous case, like in the previous slide, like what is the formula for the stress development?
for the internal stress, you are saying.
Yes, sir.
I think this question has been asked in ES only. So theoretically they have asked. No formula they have asked.
Okay.
So that is like they have asked like if there is thermal gradient exists, so there would be no stress in the body. Internal stress would be there, like that they have asked. So that's why. So thermal stress with the permitted expansion. So here what would be the case? Like this is the L, and here some expansion is permitted, and let's suppose this is the delta. Now here we have to increase temperature only, right? Decrement in temperature is nothing, because if you decrease, then it will simply go back. No issue. If you increase the temperature, then only stress will come, right?
Yes, sir.
Hmm. So when we increase the temperature, so its tendency to increase, and it will go here. L alpha delta T increment would be there, but this this total resistance would not be there for the whole L alpha delta T, right? Resistance is for only L alpha delta T minus delta, right? Hello. Because this delta, it can easily expand. No resistance is there, right?
Yes, sir.
So this much resistance is there. So now it may ask like how much. Two things it will ask, like what would the reaction here at the ends, and another thing is the thermal stress. So for the reaction, this delta, till this delta, no reaction is there. and yeah. So now what we'll do? Reaction would be the R L by PL by AE. Correct? Now we can find the R from here. Hello.
Yes, sir. Yes.
Is
Yes.
it okay to everyone or not?
Yes. Got it.
So actually, whenever thermal stress type of problem will be coming, first you have to draw the simple case. Then we have to just simply L alpha delta T, it is decreasing or increasing, that you take care. And if permitted expansion is there, then took that and simply solve the problem. Do not learn the formula here. If we are going with the learning formula, then question will never be happening. So simply with the basics we will go. So in the next class, we will solving problem like some force will apply here, and then we'll say like how much of the reaction would be here. That type of problem we can see. So one problem I will be giving for the homework, one that you take.
Sir,
Uh-huh.
Okay.
sir, in this case, thermostat will be
The thermal stress would be there.
okay, sir.
But if like temperature we have increased, like it would be less than the delta. If whole alpha delta T is less than the delta, then no thermal stress will be there, right?
Yes, sir.
So that we have to check first, because how much delta T have we have increased, like how much the value of. That's why I said like first draw this case, and then only you can know. If directly you started like L alpha delta T minus delta is equal to R L by A, trying to find the R by A, then they may not, this may not work. You first have to see like L alpha delta T is more than the delta or not. That you have to see first. If that is not there, so simply you can say thermal stress would be 0. Got it or
Yes,
not?
sir. Yes, sir. Got it, sir.
Okay, then
Sir, in our thermodynamics PPT, I couldn't find the annotations. I don't know.
actually I was looking like someone used to delete that there from there. So today, last time when I saw, like it is showing like a file has been deleted. So again I will
Yes.
upload. So no issue. And apart from in the same folder, I will be sharing one link. So in the same folder, the thermo PPT and both PPT would be there. Okay, that link 1 minute I am sharing.
Sure.
Actually, last 1 minute. I will stop the recording.
Recording video link, sir. Drive link.